So remember, the last lecture introduced the idea of sampling error. And what we want to do is realize that as we pull from underneath the population, we produce a sampling distribution of means. And essentially, what this is a distribution of sample means, and it has certain characteristics. So this distribution is approximately normal, meaning that it has that nice symmetric unimodal bell shape, and its mean is equal to the population mean. The variability of the sampling distribution is smaller than the population or the sample, and it's used to assess the likelihood of observing a given mean from the sample. So let's look at some illustrations of this. Here I have a sampling distribution of 100 random samples that are taken from a hypothetical population in which the mean is 99.75 minutes. Okay? And the mean of means is 100.4. And what I can see here is that the population mean, okay, of 99.75, that's what I observe overall. Okay? But all of these different samples here are different a little bit from this 99.75. Okay? So this is figure 6.2, part B in your textbook, and it's a very useful illustration. So if we want to look at it this way, okay, this is a normal curve, okay, in which all of these observations exist. Okay? And if I just pull randomly one sample out of there, that's going to give me a sample mean of 100.4. Okay? Likewise, I could pull another one out of there, okay, in which I could get a sample mean of 96. Okay? The overall point is that this sample of 100 random samples comes from a population that's distributed around a mean of 99.75. And the mean of the means, if I were to add up all of these means and divide by the total number of samples, would come up to 100.4. So as I can see, this is not completely equal, but it's equal enough to assume that these two parameters are equal. Now, in a population distribution, okay, this might be what I observe. Okay? I might have a skewed distribution. So in this example, I have some positive skew happening here. So in my distribution, my population variable is positively skewed. Now I can have a sample distribution, okay, where I have one sample with 200 participants. And I can see here that it kind of mirrors the population distribution in that I have some positive skew. Okay? But once I look at the observed sampling distribution for 100 samples, then I can see here that I've kind of removed the influence of that skew. And that corresponds to the idea that the theoretical sampling distribution for infinite numbers of samples is normal, even when the population distribution is not. And this is a critical element of what's known as the central limit theorem. This allows us to make inferences about populations, even if they're skewed. Okay? So the logic of inferential hypothesis testing is based on this idea of a normal distribution that we can associate with percentiles along this axis. To the extent that we have a skewed population, the math underlying those percentiles starts to break down because we can't talk about areas under the curve with the same certainty. But the central limit theorem tells us that if we theoretically sample infinite samples from underneath that distribution, that is going to normalize our distribution, and that's a very important point. Now, the normal curve is a probability distribution. So that means that given the mean and the standard deviation, we can find probabilities. This is table A that we're used to. When we're working with sample means, we can solve for these probabilities for sample means and not just individual values, and that we still use table A to do that. Likewise, the probability that we'd observe a given score, okay, starts to decrease the extent to which we get out towards the tails of the distribution. Okay? All else being equal, a score is going to be much more likely if it's closer to the mean than it is if it's farther away from the mean. So we can find the probability of any sample mean by solving the z-score for the mean, which is illustrated on page 99. And then we can use table A to solve for those individual probabilities.